Hello class, welcome to the Stat 215 Lecture 8 video. In this video, we are going to define the expected value of a random variable and use this definition to find the expected values of various random variables. Let us start our understanding of this concept with an example. Suppose we flip a fair coin 2 times. We would understand the sample size to be heads, 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 tails, tails, heads, or tails, tails. Now let us suppose that x equals the number of heads. If we were to find the corresponding probability for the possible number of heads, we would see that the probability of x equals 0 would equal 1/4. The probability of x equals 1 would be 1/2, and the probability of x equals 2 would equal 1/4. We can clearly see these probabilities from our sample size, sample space. For us though, we have to ask the question, how many heads would we expect? Now, looking at it without having a true definition of expected value, we could say that heads, tails, and tails, heads both contain 1 head, and it has the largest corresponding probability, being 1/2. So without knowing the definition of expected value officially, I would still lean with the answer of being 1 because it's the one that has the highest probability of occurring. Let's see if that actually turns out to be true. So when we are trying to understand the mean of a list of data, we know that we add up all the values and divide by the sample size. However, when we are trying to find the mean of a random variable x, for that, it's if we know the probability distribution, what is the average value of x? We call this the expected value. So what is the expected value? It is the mean of a random variable x. Now, because we are working with cases of both discrete and continuous variables, we should expect, pun intended, that we are going to have different formulas for the 2 different cases. So to begin, let x be a random variable with probability distribution f of x. Then the mean or expected value of x is mu equal to e of x equal to the summation over x of x times f of x if x is discrete. When x is continuous, our expected value will be the integral from -infinity to infinity of x multiplied by f of x dx. Let's start by looking at a few examples of the discrete case before moving on to the continuous case. To begin, let's take a look at that motivating example we looked at earlier. Once again, suppose we flip a fair coin 2 times. Our sample size, once again, is heads, 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 tails, tails, heads, and tails, tails. We let x equal the number of heads, and we calculated the probability of x equals 0 to be 1/4. The probability of x equal 1 being 1/2, and the probability of x equal to 2 to be 1/4. Using our formula for the discrete case, e of x equals the summation over x of x multiplied by f of x, we can find our expected value in this case to be 0 multiplied by its corresponding probability of 1/4 plus x equal to 1 multiplied by its corresponding probability of 1/2 plus x equals 2 and it's multiplied by its corresponding probability of 1/4 to give us an expected value of 1. So it looks like what we were expecting to occur was in fact the expected value. It's kind of nice when that works out. Let's take a look at another example. Let x represent the number of tires with low air pressure on a randomly chosen car. The probability distribution of x is given by the following, where x equals 0, 1, 2, 3, 4. Notice that we are contained within these bounds. because a car in general has 4 tires, and so at most we could have 4 tires with low pressure. At the least, we would have 0 tires with low pressure. So the probability of no tires needing air is 0.1. 1 tire needing air is 0.28. Probability of 2 tires needing air is 0.33. 3 tires needing air is 0.2. And we were not given what is the probability of 4 tires having low air pressure, but we know that that's actually a pretty easy value to calculate. So given that in a probability distribution, we know the summation of the probabilities must be equivalent to 1. So if we take that known value of 1 and subtract it from the probabilities that we do know using our knowledge of the complement rule, we can find the probability of 4 tires being with low air pressure. Using our skills of adding and subtracting, we can find that the probability of 4 tires needing air to be 0.09 or 9%. Now that we've gone over that hurdle, we can now find the expected value of x. So to do, we must recall that the formula for finding the expected value of x in the discrete case would be to take the summation over x of x multiplied by f of x. Doing so in a chart like this is pretty simple because we just need to multiply our columns and then, so multiply our columns and then add them together. So this would be 0 multiplied by 0.1 plus 1 multiplied by 0.28 plus 2 multiplied by 0.33 plus 3 multiplied by 0.2 and finally 4 multiplied by 0.09. Adding up our products, we will have an expected value of 1.9. So we should expect, at least theoretically, that 1.9 tires, which since we can't technically have a fraction of a tire, we could say that about 2 tires need air. Let's take a look at a third example. A salesperson for a medical device company had 2 appointments on a given day. For the first appointment, he believes that he has a 70% chance to make the sale and earn $1,000 in commission. For the second appointment, he believes he has a 40% chance to make a sale and earn $1,500 in commission. Assuming the results of the meetings are independent of each other, what is his expected commission for the day? All right, so in this case, even though it's not what we can traditionally use for our probability distributions, we can still pretty easily find the expected value. For us, we have 4 possibilities. 1, that he makes no sale on either opportunities. Second, he has a sale for the first option, no sale on the second, meaning he would earn $1,000. Third, no sale on the first event, but it makes a sale on the second opportunity, meaning he would make $1,500. Or he would be able to make a sale on both opportunities, meaning he would earn a combined $2,500. From there, we can, we can treat the amount of money as earned being our value of x, And our understanding of our independence, where the probability of A and B equals the probability of A multiplied by the probability of B, to find the corresponding probabilities of each event. We know the probability of our salesperson getting a sale for the first event is 0.7, meaning the probability that his sale is unsuccessful would be 1 minus 0.7. The probability that he is successful in his second sales attempt is 0.4, and the probability of his failure in the second attempt would be 1 minus 0.4. We can see the specific calculations for each of our 4 possibilities below. Using our knowledge, we can then find the expected value. So 0 multiplied by 0.18 plus 1,000 multiplied by 0.42 plus 1,500 multiplied by 0.12 plus 2,500 multiplied by 0.28. This will give us an expected commission of $1,300. Not bad for a day's work. So at this point, we've done 3 examples for the discrete case. So at this point, I think we're probably comfortable enough with our discrete case to move on to continuous. Let's take a look at a first example. A dealer's profit in units of $5,000 on a new automobile is a random variable x with the density function f of x equals 2 multiplied by the quantity of 1 minus x on the bounds from 0 to 1 and 0 otherwise. What would our average profit per automobile be? Let us recall that in the continuous case, our expected value is the integral from negative infinity to infinity of x multiplied by f of x dx. Using our knowledge from the problem, we know that f of x equals 2 multiplied by the quantity 1 minus x, but only on the bounds of 0 less than x less than 1. This means that for our expected value, we will integrate from 0 to 1 of x multiplied by 2 times the quantity of 1 minus x and quantity dx. To do some quick simplification, we will integrate from 0 to 1, 2x minus 2x squared dx. Now to perform our integration, we will have x squared minus 2x to the third over 3. Take that from 0 to 1. Simplify. 1 minus 2/3 minus 0 minus 0. And this will give us 1/3. Excellent. Now, going back to our problem. So a dealer's profit in units of $5,000 on a new automobile is a random variable x with a density function. So we can expect of that unit of $5,000 to get a fee that is 1/3. So 5,000 times 1/3 would be 1,667. Once again, not bad. Now I do want to say that this last step is unique to the problem. We don't necessarily need to do it. The only reason, or rather we need to do it in this case because we were told that the units were in terms of $5,000. If that had not been the case, then our expected value would have been left alone at 1/3. So at this point, let's take a look at this concept of g of x. So let us consider the discrete random variable x with the probability distribution f of x for x equal to -1, 0, 1, and 2. Now we'll suppose that we let g of x equal x squared, which would then imply that g of x has the possible values of 0, 1, and 4. Where are we getting that? Well, -1 squared would be 1, 0 squared is 0, 1 squared is 1, and 2 squared is 4. So this means, once again, that our possible values of g of x are 0, 1, and 4. Now to understand the probabilities of such an event, well, the probability of g of x equals 0, it would be the case of f of x equal to 0. The probability of g of x equal to 1 is the case when f is -1 or f of 1. And the probability of g of x equal to 4 is when f of x is, or excuse me, when x of f of x is 2. So in order to find the expected value of g of x, we would still use our understanding of our formula, where the expected value of x is x multiplied by its corresponding probability. That still hasn't changed, only instead of x, we now have g of x. So we know that our possible quantities for g of x are 0, 1, and 4. And we know from our previous slide, when g of x is 0, its corresponding probability is f of 0. When g of x is 1, its corresponding probability is the f of -1 plus f of 1. And the corresponding probability when g of x is 4 is f of 2. So, with a little bit of simplification, we can still see that our expected value of g of x is going to be the summation of x, or excuse me, the summation over x of g of x multiplied by f of x. So let's take this a step further and define things officially. So let x be a random variable with a probability distribution f of x. The expected value of the random variable g of x is, in the discrete case, meaning when x is discrete, the expected value of g of x equals the summation over x of g of x f of x. When x is continuous, the expected value of g of x equals the integral from -infinity to infinity of g of x f of x dx. Let's take a look at another example. Let x be a random variable with the following density function, where f of x equals x squared over 3 on the bounds of -1 less than x less than 2, and let it be 0 otherwise. We would like to find the expected value of g of x, which is equal to 4x plus 3. As always, I do like to write things down. So f of x, you may recall, is x squared over 3 on the bounds from -1 less than x less than 2, and g of x equals 4x plus 3. We know generically that the expected value of g of x equals the integral from -infinity to infinity of g of x f of x dx. applying that to the case before us, we are trying to find the expected value of 4x plus 3. This would mean that we will integrate from -1 to 2 of 4x plus 3, which is our g of x, multiplied by our f of x, which is x squared over 3 dx. Now we can simplify. Once again, we will still be integrating from -1 to 2, and our simplified expression will become 4x to the third over 3 plus 3x squared over 3 dx. Now we are involved in a simple integration problem. So integrating from -1 to 2, we have x to the 4 over 3 plus x to the third over 3. Now we can plug and chug. So 16 over 3 plus 8 over 3 multiplied by the quantity of 1/3 minus 1/3. This will give us 24/3 or 8. So the answer to what is the expected value of 4x plus 3, the answer is 8. Not bad. Let's try another one. But before we do that, let's take another step of difficulty. Let x and y be a random variables with a joint probability distribution f of xy. The expected value of g of x comma y is, in the discrete case, the summation over x, the summation over y of g of xy multiplied by f of xy. In the continuous case, we will have our expected value of g of x comma y be the double integration from -infinity to infinity of g of x comma y multiplied by f of x comma y dx dy. So let's start with an example 6, which is from our PENS example from our lecture 7. So we're going to let g of x comma y be x multiplied by y. So we now want to find the expected value of g of x comma y, which implies we are going to want to find the expected value of x multiplied by y. So using our table, we see that our possible values of x are 0, 1, and 2, and our possible values of y are also 0, 1, and 2. And our corresponding probabilities we have inside our table. This means, using our formula, the expected value of x times y would be the summation from 0 to 2, the summation from 0 to 2, x multiplied by y multiplied by f of the quantity x comma y. Which means essentially we would multiply 0 times 0 multiplied by its corresponding probability of 3/28 plus 0 times 1 multiplied by its corresponding probability, so on and so forth, until we have every possible combination, and we have an expected value of xy that is equivalent to 3/14. This is one of those problems that, while not mathematically necessarily hard to solve, it is rather long to solve. Let's take a look at a continuous case. Find the expected value of y over x for the following density function. where f of x comma y is x multiplied by the quantity of 1 plus 3y squared all over 4 on the bounds from 0 less than x less than 2 and 0 less than 1 or less than y less than 1, and let it be 0 otherwise. So to make our life easier, I would like to rewrite our density function. So f of x comma y equals x multiplied by the quantity of 1 plus 3y squared and quantity all over 4, and the bounds from 0 less than x less than 2 and 0 less than y less than 1. So now we can easily set up our problem where the expected value of y over x, we would first integral for y, so 0 to 1, integral over for x, 0 to 2, by our g of x function, well, g of x comma y, which is y over x, and our f of x comma y function, so x multiplied by the quantity, 1 plus 3y squared over 4 dx dy. Let's begin with a little bit of simplification. So once again, we have the integral from 0 to 1, the integral from 0 to 2, and we will have y over 4 plus 3y cubed over 4 dx dy. So let's start by integrating over x, because we remember when we perform double integrations, we start from the inside out. So working on our way from the inside, quick integration, this would become xy over 4 plus 3xy cubed over 4 on our bounds from 0 to 2. I'm going to skip this middle step to try to get this all on this single slide. So this would simplify to be the integral from 0 to 1 of y squared, or excuse me, y over 2 plus 3y cubed over 2 dy. Now a much simpler integration problem. Integrating over y, we have y squared over 4 plus 3y to the 4th over 8, which will simplify to 1/4 plus 3/8, which will equal 5/8. So the expected value of y over x equals 5/8. Whew, that was a lot. You may want to try that one again for a practice on your own. So this does bring us to the end of the lecture though. Quick summary. So let us recall that the mean of a random variable is also known as the expected value of a random variable. When we are dealing with a discrete variable, we let mu equal e of x equal the summation over x of x multiplied by f of x, and when x is continuous, our expected value is equal to the integral from negative infinity to infinity of x multiplied by f of x dx. And we are also quite able to find the expected value of g of x and the expected value of g of x comma y. All right, that brings us to the end. Have a good night.